Weak acids and bases. So, not getting super fancy on this one. Dang it, that stupid countdown. All right, here we go. Weak acids and bases. The big difference about strong acids and bases from weak acids and bases is how much they dissociate. So, the biggest thing that we've been talking about are strong acids and bases. They fully dissociate into their constituent ions. So, there's no equilibrium constant with that. And they are going fully into their respective ions, which makes calculations pretty easy. Weak acids and weak bases are ones that do not dissociate very well. And so what we're provided with is an equilibrium constant. Okay, so they're treated just like what we did with last chapter. And we have a few steps that we can go along with that. Okay, this is from the textbook, and I think it describes it pretty well. If you were to describe something as a Ka value of very, very large, then it's going to be a strong acid. So this is our equilibrium constant of A, which is an acid in this case. So it's far to the right. With most of our strong acids and bases that we've talked about to this point, we're talking about something that is pretty much complete. When we deal with a weak acid, it's going to be more to the left. It's going to be staying more its reactants, and it's going to have a much, much lower concentration of hydrogen ions or hydronium ions than what we do for our original acid. That's what the HA stands for. Lots of funny jokes I could make. Actually, it probably wouldn't be funny. In this case, we have an equilibrium concentration with a concentration of H compared with the original concentration of HA. And so this could be all kinds of different amounts. Okay, but your concentration of your acid that you start with is going to be about the same, which we've worked with some of those already. For example, if we said something was a 0.1 molar solution of nitric acid, which is HNO3, and it wants to know the pH of that, you know that our pH of our hydrogen concentration after it dissociates is pretty much equal to what our original acid concentration. So you would take the negative log of that 0.1 molar. Okay, and also another thing is these have a much weaker conjugate base to a strong acid, and the weak acid will have a conjugate base that is stronger than water. All right, to do this, what you're going to do is you're going to list different things. And you might have two substances that have different equilibrium constants, and you're going to be comparing this to water and seeing which one would be more likely to give up a hydrogen or not. Okay, you're going to have your one that's going to produce more hydrogen. You're going to write the equilibrium expression just like we did in the equilibrium unit. You're going to do an ice table just like we did before, and you're going to solve for the unknowns. One thing to keep in mind is if we have a very, very small equilibrium constant, so think about water. We've been working with water, and its equilibrium constant is, 1 times 10 to the negative 14th. So what's it going to do? It's going to stay mostly water. So the amount compared to the original water that it's missing is effectively zero. Okay, so negate that away from your original and solve for x. And that should make your calculations very simple. You're not going to be doing quadratics or anything. Okay, here's an example. If we were to calculate the pH of a 0.5 molar aqueous solution of a weak acid, it gives us our Ka here, 7.2 times 10 to the negative fourth. You might notice that this is more dissociating than it is with water. Okay, so if you have to compare it to water, hydrogen fluoride or hydrofluoric acid and water are the major species because the EQ constant lies towards the reactants. So an aqueous solution means that it's in water. Kw is 1 times 10 to the negative 14th, the one that's more likely to give up any usable amount of hydrogen ions that we could take then the pH of would be HF, okay, because its acid constant right here is much, much larger than the one of water. So you can write these out. I'm sorry, I have some of these lines. I didn't animate every single part. It'll make sense in just a minute. All right, we do our ice table. We start off with about 0 hydronium and 0 fluoride. We have 0.5 molar hydrofluoric acid. We minus X here, and we add X on each one of these. And we have a 1-to-1 ratio of hydronium ions that we're producing for every fluoride ion that we're producing as well. And at equilibrium, we have 0.5 minus X, and over here we have X. what you're going to do is you are going to negate the x here, because compared to 0.5, we're dealing with something that is to the negative 1, 2, 3, 4. It's going to be very small. But compared to 0, it's something over here. Hopefully you still recall how to do those correctly. You write your expression, the hydrogen ions or hydronium over and fluoride over HF. And so we have XX over our HF. We negate the X, and we have basically X squared over 0.5. You solve for that, and we have X equals 0.019 molar. And you take the pH of that, and it's 1.72. So it's a weak acid, but still got a relatively low pH. So if we're looking at something called percent dissociation, or how much of it ionizes, we can calculate another variable with this. Okay, so if we had 0.019 molar over our original times 100. So this is like calculating your grade, right? So you have so many right over your original, which would be like 100, and you multiply that percent, and you get whatever your percentage would be. Okay, so it's the amount dissociated over the initial concentration. And so your percent dissociation in this case is 3.8%. So you might have noticed that even in various other weak acids, they'll have them dilution ratios and how much is actually dissolved. Okay, let's look a little bit again about how Le Chatelier deals with this. So if you have an equilibrium constant, it's not going to change with our molarity change. It only changes with our temperature. We talked about that. Your equilibrium constant for water, for example, is 1 times 10 to the negative 14th. No matter if you have a huge amount of hydrogen ions or a very small amount of hydrogen ions, that constant stays the same. However, if you remember too, when we've changed the temperature of water, that constant then changes. So the percent ionization does change when the molarity value. So if you have a high molarity, that's going to change your constant or your percent ionization. So if we dilute this, all molarity values decrease. For an acid dissociation, the numerator decreases more than the denominator, right? Because we have 2 species up here and only 1 down here. So our Q is going to be less than K, and our reaction shifts to consume more reactant to make more product. So what happens is, if we dilute things, it's actually going to make more product because it's going to want to dissociate a little bit more. Let's see. With this, weak bases, this is basically saying weak bases, we do the same as what we would for weak acids. A couple AP style questions. I'm going to break that down into another video, so that way it keeps it a little bit smaller.